So they are linearly independent. However, I didn't say yet what are linearly independent solutions and something about the solutions. So let me, just before we continue this, I'll just put here like solutions, okay? Now, the following is a theorem about second order linear differential equations. So we have theorem 1, which says that if we have y1x, y2x, both of them are solutions, so being solutions of the second order linear equation, so with constant coefficients or in general, so even with variable coefficients of let's say I will just put here the general case with of homogeneous second order equation with constant coefficients. Then for every C1, C2 from R, C1 y1 of x plus C2 y2 of x is also a solution of, I'll call this star, so of star. Okay, so that is when we have two solutions of this equation, every linear combination of them is also a solution. Now there is another theorem also, theorem 2. We will not prove neither of these theorems in this video, because we ask, okay, what is the general solution? Okay, and the following theorem first, the following theorem says if we have two solutions, y1, y2, of the equation that we discuss, and they are linearly independent, and A is always different from 0, then the general solution is given by yx equals, this is what we just saw, C1, C2, any real numbers. Now I will just explain what does it mean linearly independent in case you haven't seen that concept. So you have seen about vectors. Basically these are regarded as vectors, just in different space. So y1, y2 are linearly independent means neither, neither y1 nor y2 is a constant multiple of the other. So for example, you see, if we have we have y1 equals x, y2 equals 5x. These are linearly dependent. Not independent, dependent. Okay. Why? Because y2 equals 5 times y1. You can see that. However, if we have y1 equals e to the power 2x and y2 equals e to the power 4x, even though 4 is multiple of 2, these two functions are not. These are linearly independent. So for different, I'll just put for different a and b, e to the power ax, e to the power bx are always linearly independent. So this is always the case. So these functions are never constant multiple. We cannot find a constant multiple to get from e to the power 2x to e to the power 4x. There is no times something, some number, okay, some number. That's just the nature of the function. And this is very good because we can now show this case here. I am going to copy this. I'll just cut it here. So now when I have this, so I have b squared minus 4ac. So that means that I have r1 equals minus b plus b squared minus 4ac over 2a. So they are real and different. Minus b minus b squared minus 4ac over 2a. Of course, I don't need to write this, you know. But they are different, so r1 is different from r2. So if we have y1 equals e to the power r1x and y2, if we put this, so this is solution, and e to the power r2, this is also a solution. So if we plug in this, you can pause the video and check that these are solutions. So they are solutions, but they are also linearly independent. And according to the theorem 2, the general solution is c1 e to the power r1x plus c2 e to the power r2x. That is exactly what we have in our table as a first row. You see, this is what we have proven. So if b squared minus 4ac is strictly greater than 0, we have two different real roots and two corresponding, for each root we have the corresponding solution. But as we have seen here, so this is important. This is the basis for this part. Then they are linearly independent. So each such two solutions are linearly independent when we have different, and therefore Therefore, the general solution is by the theorem 2 here. If they are linearly independent, then the general solution is has this form. Okay, let us do the second case. Second case says that discriminant is the same as discriminant is 0. In that case, we have r equals minus b over 2a. So we know that y equals is a solution. And now let us take y2 to be y1 prime, which is sorry, not that, that's something else. X e to the power rx, and we will show that that is a solution. So we plug in into the equation. We take the derivative plus r squared x rx plus b x plus rx e to the power rx plus cx. Okay, and that is now 2ar plus b e to the power rx plus squared plus br plus c e to the x rx. Now we know that this is 0 and this is also 0 because b squared minus 4ac is equal, so r equals minus b over 2, or if you want 2ar plus b equals 0. So both of them are 0. Okay, and we also see that y1, y2 are linear. So this implies that y2 is solution also, is also a solution. We just saw that. So y1, y2 are solutions, and they are independent plus linearly independent. Okay, so therefore the general solution is c1 e to the power rx plus c2x e to the power rx. Well, this is the general solution. And if you go back to the table, I'll show you now, that is the second row here. So we have proven this. Okay, and the third case is when the discriminant is less than 0. So the roots then are complex, so we'll have r1 equals alpha plus I beta, and r2 is alpha minus I beta. And in fact, alpha is minus b over 2a. Alpha and beta is square root 4ac minus b squared over 2a. So we use the Euler's definition or the relation for the complex numbers, the Euler's form of complex numbers. And let us see what we get. So y is, and they are linearly independent because alpha and beta are different real numbers, here real numbers. So then y is c1 e to the power plus c2 e to the power r2x. Now let us substitute. So c1 r1 is alpha plus I beta x, and e to the power alpha minus I beta x. So that's equal to c1 e to the power alpha x I can write here e to the power I beta x, okay? And then we use this relation here, which gives us, I will not write fully, I'll just open the bracket, that's cosine beta x plus I sine beta x plus c2, and here the same thing, e alpha x cosine beta x, but here is now minus because of this minus here, minus I sine beta x. We can rearrange that, that will be c1 plus c2 cosine beta x plus I c1 minus c2 sine beta x. And now we put this as some c1 and this we put as some small c2, so the final is, the form is cosine beta x plus c2 sine beta x. Okay, and that is how we obtain the solution in the case of when the roots are complex. So we have proven this as well, and you can see that's this one. Okay, so this is the second, so more theoretical part, and in next video we are going to see how to solve a non-homogeneous linear equation of the second order with constant coefficients.